Hello once again, AP Calc BC students, Mr. Record here from Avon High School. And this is our finale problem, our end to our wonderful conversation about that elusive topic of the Lagrange error bound that sometimes gives kids a lot of trouble. But, if you really kind of dig deep, look at that equation, that Taylor's inequality, it doesn't seem to be quite as daunting. So this is our topic 1012 from the notes that I use with my students, example 6. It's another AP style question. This time it's going to illustrate a table, and it's got more of a proof vibe to it, very similar to what you might see on the exam. And might I add, it is not going to allow you to use a calculator, but fear not, I think you're going to be able to handle this. So let's read the question here very quickly. It says, let h be a function having derivatives of all orders for all real numbers with values of the absolute value of the fifth derivative of h of x shown in the table above. If the fourth degree Taylor polynomial for g about x equal 1 is going to be used to approximate h on the interval 1/2 to 1, show that the Lagrange error bound for the maximum error in approximating h of 0.5 on that interval 1/2 to 1 is less than 1 over 1200. It's a little scary when you see that fraction, but you'll be surprised that you're going to be able to take care of this with no trouble at all. But as I said before, it all starts right down here below, right? We've got to know that Taylor's inequality, right? This thing just drives about every Lagrange error bound problem that you're going to come across, okay? So one of the things that I like to tell my students to do is maybe underline some of your key players. If we know that we're looking at a fourth degree Taylor polynomial, that means that our n throughout that formula is going to be 4. This is the part that can be a little confusing. This is telling us that our Taylor polynomial has been centered at 1. You're going to want to say that c is 1. You don't want to get fooled into thinking that's your x value, because the x value is the value that you're approximating your function h at, which in this case is 0.5. So I think we've got all of our key players there. We can just start from the left side of that inequality, which is the absolute value of r sub 4 evaluated at 1/2. That's our error that we're looking for. And so we say that that is less than or equal to another quite hefty absolute value. This one features the maximum of, well, instead of the nth plus 1 derivative of f, this would be the nth plus 1 or fifth derivative of h, evaluated at that elusive z. And sometimes I show my students that that z is just going to fall between the 0.5 and the 1. It's going to fall between your x and your c, but more often than not, we don't even care about that. We don't even use that z. All of this is being reinforced by what our table is presenting us anyway. We're going to take all that and divide by 5 factorial and multiply by x minus c. Why not? Let's go ahead and plug in our x minus our c like that. And you might notice that this is written in a way that it's going to give a negative answer even once we take it to an odd power, but the absolute values are going to turn everything back into a positive like our error should be. And so now the next thing to do is just kind of see where this takes us. So what is that maximum value of the fifth derivative? Well, on the interval 0.5 to 1, we just got to look through all of these numbers and say, what seems to be the largest value there, right? And so we're going to go ahead and assume that value to be 2. And I believe that there could be some issue here where you could read a little too much into the problem and think, is there a chance that maybe a fifth derivative might be a little bit, could there be a 2.1 somewhere in the middle? And maybe it wouldn't be a bad idea if the directions said the fifth derivative of h values are increasing, just so that we are aware of that. But in this case, we're going to go ahead and rely on 2 being that maximum. 5 factorial we know is 120. 1/2 minus 1 is our 1/2 to the 5th power. And you're just going to have to somehow get to a point where you're confident enough that that's going to be equivalent to 1 over 1200. Now, here's a little tip here. I see a 120 here that I might want to be a little bit reluctant to reduce down. So how about we do this? 2 to the 5th power is going to be 32, right? So let's drop down that 120. And let's take that 2 over that 32 and reduce them like that, right? Now you might wonder, well, why didn't I reduce the 2 over 120 to get 1 over 60? You could. I just thought that 60 times 32 was a little harder to kind of infer from than 120 times 16, because I feel quite confident that I can make this statement. And the reason is because that 16 is larger than 10, right? Because 120 times 10, of course, would be 1200. And the bigger the denominator, obviously the smaller the fraction. And so that is exactly what we could put on our AP exam to really hammer the point home that we've proven that our error is going to be less than this given 1 over 1200. I sure hope these videos have helped out a little bit. If you hadn't had a chance to check out some of the early ones, please do so, especially examples 4, 5, and 6, because I think those appeal to the kinds of questions that you're most likely to see on the Advanced Placement Calculus BC exam. It's been a joy working with you guys and producing these videos, and be sure to check out some of my other ones and just keep studying, because the Lagrange error bound doesn't have to be quite as difficult as you think. We'll see you next time.